So let's have a look at interpreting intracellular electrophysiological data. So current clamp data, I would argue, is the easiest data to interpret by and large, right? Sort of what you see is what you get, right? Here is some current clamp recording from a neuron. They're applying some current. So this showing here is the current that they're applying to the neuron. This is the current clamp, right? They said zero current, then they're saying 100 picoamps. Zero current, then 200 picoamps. Zero current, actually, it's not quite. Now it's zero current and 200 picoamps, right? So they're applying these steps of current into the cell, and the neuron is firing more and more, or faster and faster action potentials, firing action potentials at a higher frequency. So a disease or a drug treatment may make a cell more or less excitable, which means it may need more. More excitable means it needs less current to fire. So for instance, this is just some recordings from an amyloid beta expressing animal, and you can see that this is the frequency at which the cell is firing action potentials. This is how much current they're injecting. The black is control. So normally, if they put in 300 picoamps, the neuron fires at about 3 hertz, 3 times a second. But in this amyloid beta condition, they put in 300 picoamps and the neuron fires at 6 hertz. So the amyloid beta has made the cell more excitable. Um, it fires more action potentials in response to less input. Now, very easy to interpret all of this, but the point is that we have no idea why. Why is it doing that? What has changed? And we'll get on to something about that. Now, the other thing that you can measure with current clamp is the resting membrane potential. So for instance, here is a neuron, it's firing action potentials tonically, which is to say sort of constantly without any input. And then they apply baclofen, the GABA B agonist, the GABA B receptor agonist, and the neuron hyperpolarizes. Then they remove the baclofen and it starts to wash out of the bath that this bit of brain is sitting in. And then the neuron depolarizes and starts firing action potentials again. So again, excuse the spelling mistake there, again, we get this clear interpretable data that if a human was to eat baclofen, all of its neurons would rest at a slightly lower potential and fire less action potentials. But again, we have no idea why. What has happened? Now, we can probe this a little bit more deeply, and this is what I was talking about before. So here is a similar experiment. They are applying baclofen, and you can see that the thick black line is the resting membrane potential, and the cell hyperpolarizes. But what they're doing here, these little vertical lines, this is because they're injecting a little bit of current, a little bit of negative current, and they're getting a change in voltage. Right, so they're injecting negative current, it hyperpolarizes the cell, and in A, so before the baclofen has got on, they get a bigger change in voltage than they do when they're applying baclofen, where they get a smaller change in voltage. And we know that resistance is equal to V over I. So the V has gotten less, i.e. the change in voltage has gotten less. The I is the same, they're still injecting minus 300 picoamps, so the resistance must have dropped. And what does that mean? Well, if the resistance has dropped, an ion channel has opened, or the conductance has increased, the membrane conductance. And now this should all of a sudden start to look very similar to a lot of the questions that I asked you in CHP 311. We have a cell where we know the resistance has decreased, the conductance has increased, and it is drawn in the negative direction. And we know that the equilibrium potential of ions, potassium is going to be minus 90, chloride is going to be about minus 60 or 70, and sodium is going to be positive 40. Well, it plainly can't be sodium, because if sodium channels were opening, it would bring the cell in a positive direction. Maybe it's chloride, but chloride is unlikely to be able to hyperpolarize the cell by 10 millivolts, so it's going to be potassium channels opening. And of course, that is what GABA B receptors do. Indeed, you can take that even further by doing this kind of experiment. So here they are puffing on, just applying a little bit of baclofen to the cell. And when they are at minus 50, they get a hyperpolarization, minus 55 hyperpolarization. By minus 65, the hyperpolarization is getting smaller. By minus 75, it's getting very small. And by minus 85, it's hardly there. And so they've plotted this in a slightly funny way. But the point is that the amplitude of the response is dropping to zero when they're at about minus 90, i.e. there's no current flowing when the cell is at minus 90. And what is the definition of the equilibrium potential? Where no current flows. So the ion channel that's mediating this has an equilibrium potential of minus 90. What ion does? It's potassium. So voltage clamp, on the other hand, can be very tricky to interpret to begin with, right? So in voltage clamp, our amplifier tries to keep the membrane potential to whatever we set it to, and that set voltage can change, on a dime. We can say stay here, then up there, then there, if it's going to be useful. And so in order to do that, the voltage clamp amplifier must apply a current equal and opposite to the transmembrane current. And so we know what the transmembrane current is because it's equal and opposite to what our amplifier is doing. And so this is the kind of stuff that you can see. So in current clamp, we record an EPSP, while in voltage clamp, we report an EPSC. And they go in opposite directions. And really, that's just by convention. By convention, we report what the amplifier does, not what is happening to the membrane, right? So this is equal and opposite to what is going through the membrane. So we see this negative current, which is known as an inward current, because it represents positive charges moving into the cell. And surprisingly, potentially, the EPSC is much more brief than the EPSP. Well, how can that be the case? Because of membrane capacitance, because it's this current charges up the capacitor and then the capacitor decharges slowly. And we see the same thing with IPSP. So here's an inhibitory postsynaptic potential going down the page. We've got the cell at minus 50, so this will be a chloride current. And if we then voltage clamp the cell at minus 50, we can see the current, this outward current. And just like sort of we talked about, you can use this to measure the equilibrium potential. And so we can do that with sort of relatively normal chloride concentrations. So 10 millimolar on the inside, which of course is easy to do when we're doing patch clamp recordings because whatever we put in the pipette spills into the cell. So here we are recording the current, and so we have a current going in one direction. This is the membrane potential, and as we go from minus 60 to minus 70, the direction of this current reverses. So this is the reversal potential, aka the equilibrium potential. It must be about minus 65, and so that's plotted over here, and bing, 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 there's the line going through minus 65. When we increase the chloride inside the cell, meaning the chloride doesn't want to go into the cell as much, the equilibrium potential is now at minus 40. Another thing that's very commonly done if you're interested in synaptic potential is to record miniature synaptic potentials. So we know that when an active potential invades a presynaptic terminal, that presynaptic terminal releases vesicles containing neurotransmitter. And connection between one cell and another cell often involves 1, 2, 3, 4, 5, 6 synapses, something like that. Maybe as many as 12, usually not much more. And so every one of those synaptic terminals, give or take, releases a vesicle when an action potential comes down the axon. But what happens when you block all action potentials? Well, occasionally those vesicles will just dock and release their contents anyway, completely spontaneously. And this is what a miniature synaptic potential or a miniature synaptic current is. This spontaneous release of a vesicle. Now, what is so useful about that is that the amplitude of these minis solely depends on the postsynaptic side, right? Because there are drugs that can change the way the presynaptic terminal works, and it can release more or less vesicles. But if it's happening spontaneously, that doesn't matter. So only one vesicle is ever released at a time. And so if those vesicles are bigger, it means that more receptors have been inserted at the synapse to sense them. On the other hand, the frequency of the miniatures just depends on the excitability of the presynaptic terminal. i.e. how much calcium is basically flooding into that presynaptic terminal spontaneously. And this is what these kind of experiments look like. So they're in voltage clamp, they're recording the frequency of miniature events. Each one of these downwards going events is right. Actually sure whether it's a miniature EPSP or a miniature IPSP, but let's say it's a miniature EPSP. Then they put on dopamine and the frequency clearly massively decreases. And then when they watch out the dopamine, it looks like it goes roughly back to baseline, i.e. the control condition. And when you do, this is a little histogram showing the how many of the minis had an amplitude of 200 millivolts or less, 400 millivolts or less, 600 millivolts or less. And you can see that control and dopamine are the same, i.e. the dopamine didn't make the minis bigger. But when you look at the inter-event interval, i.e. the time between each mini, then you get a distribution like this, and you can see that it's gotten much bigger in dopamine, so i.e. the frequency has dropped. But the real star of voltage clamp stuff is to measure voltage-gated ion channels. That's what it was invented to do, basically, certainly popularized to do. And you use specific protocols, as they're called, to reveal specific properties. So this protocol here reveals the so-called voltage dependence of activation, which is to say what is the voltage needed to open the ion channels. So you have the cell at some relatively hyperpolarized potential, typically minus 80, minus 100, and then you step the voltage up to some more positive potential, and you do that over and over again to slightly more and more positive potentials, and you see a waveform like this if you've done it properly, where this will be the smallest depolarizing potential that opens the channel, and then this is the next one, and then this is the next one, and then the currents start to appear smaller and smaller and even go the other direction. And why is that? Well, because as you make the voltage step bigger and bigger, you do open more and more channels. But at some point, you've opened all of the channels, but then you're approaching the equilibrium potential for, in this case, it's going to be sodium. And so this is what if you plot this data in A and on a graph, you see this. So you see the ion channels start to open as you depolarize above minus 40. But as you keep going, then the current gets smaller, flips over and gets bigger in the other way. Now, if instead of reporting the current, you report the conductance, then you see a much clearer signal, which is what is shown here. So this is the voltage dependence of activation. You can see the ion channel starts to open at about minus 40. It's basically halfway open if you step the cell to minus 20, and by 0 millivolts, all of the sodium channels that are going to open are open. You can also probe the voltage dependence of inactivation. So you depolarize a cell to some variable potential for a long period of time. This is what these little figures down here are supposed to show. These are showing the protocol. So you hold the cell, let's say at minus 80, or at minus 60, or at minus 40, right? And then you do this step to the potential that should open all of the channels if the channels weren't inactivated. So this is what this figure is showing. A little messy. I don't really believe this little blip at the bottom here, but the point here is that if the cell sits at minus 80 and then you step it up to a depolarized potential, probably something in this case I would guess like minus 20, then you get a big current. But if you hold the cell at a more depolarized potential, like say minus 40, then when you step the voltage open to open the ion channel, you don't get anything, right? Because all of the channels have been inactivated. So what we see here now is the voltage dependence of activation and the voltage dependence of inactivation. Now I will just point out something a little bit of interest here, which we have this little patch in here, where if you hold a cell, if a cell was able to sit at about minus 40, then this would neither completely inactivate the channels, right? So the channels could be open, but it would also open the channels a little bit. We have this little window in here where the channels can both be open and not inactivate. And this is generally the explanation of something called the persistent sodium current, right? So we've said before how The resting membrane potential of a cell is generated by this balance between um, sodium channel flux and potassium channel flux. Well, in some cells, not all, but in some cells, this persistent sodium current can become significant and be a significant source of depolarization. Now, there are millions of protocols. Um, I just wanted to show one here that I think is pretty cool, and this is the time dependence of the recovery from inactivation, right? So what they do is they do a step that's only 2 milliseconds long to just open all of the channels and, of course, inactivate them, and then a varying time after that, they apply another step, right, to open up as many channels that have recovered from inactivation as possible. And of course, if they do that step just a few milliseconds after the first one, well, most of the ion channels are still inactivated. But if they wait about 5 milliseconds, then most of the ion channels have de-inactivated. They're ready to open again. I will show something in this figure that's quite interesting, which is even after 20 milliseconds, we're still at 60%. So some ion voltage-gated sodium channels take a very long time to recover from inactivation, much longer than would be predicted by the simple Hodgkin and Huxley model. So these cells will typically fire when they receive a constant excitatory input. They will fire one action potential and then they have a big pause before they'll fire any others. Now, from voltage clamp data like this, you can look at a lot of things, but one of the best things it's useful for is looking at so-called channelopathies. So a lot of epilepsies are genetically inherited, and they involve mutations in voltage-gated ion channels. And in this case, we've got voltage-gated sodium channels. And they can be surprisingly subtle. So this is a um, voltage dependence of inactivation curve. Here you can see the little protocol that you have to sit and stare at for a while to figure out what's going on. But they hold the cell at some potential, they'll step it down to minus 120 millivolts for 100 milliseconds, or step it all the way up to positive 20 for 100 milliseconds, and then do a step to minus 10 to try and evoke a sodium current. And what you see is that, of course, as that pre-pulse potential, that step that holds the cell at varying voltages changes from minus 120 all the way up to minus 30 or even further, nearly to zero, these channels inactivate. And you can see that the wild type in black is here, and we have shifts both to the left and the right that seem to be involved in epilepsy. The voltage dependence of activation seems largely the same, though I would have to wonder if for this mutation here, R1648C, this could be the effect that's actually responsible for the epilepsy. Um, could be wrong, right? And here is the time dependence of recovery from inactivation. So you can see that it takes a long time for this recovery to get back to the current to return to normal, but there seems to be no great difference between all of these mutations.